Our next speaker is Dariusz Ratman from Roche. And we will, after Dariusz's talk, we will have another break. Thank you.
All right, thanks, Ilina. Can you confirm that you can see my screen?
Yes.
Right. Okay, so my name is Dariusz Ratman. So I'm from Roche Global IT Solutions Center, and we're an internal IT organization which supports various functions across Roche. And personally, I'm supporting Genentech early research and development, mainly in the area of our programming. And today I will tell you a bit about some of the tooling which we developed to streamline our development workflows and explain how they fit into this theme of unified R environments which we create for data analysts and scientists. Okay. All right, so working research comes with specific needs in terms of reproducibility and comparability of results. So we're not as constrained as in case of validated environments, but still, if you're doing some analysis today and you want to repeat it 1 year from now, you need to have means to get the same result. And at the same time, if you're a software developer, if you create, let's say, a Docker container for your Shiny application that does some sort of numerical analysis, the result of this analysis should be comparable to what analysts would get if he did the same thing interactively. So these are some of the key principles which we need to follow when we create these computational environments. Okay, so these shared environments we create span multiple platforms. Platforms like HPC, local machines, and more Docker and Singularity containers. And we provide them to our users through command line interfaces, through Shiny apps or Plumber APIs. And these are channeled to our users through platforms such as Shiny Server, RStudio Connect. And as we transition more and more into container-based environments, we start to rely more on general purpose platforms like Kubernetes and also on Shiny Proxy, which plays very nicely with Docker containers. So at the foundation, our R environment consists of the operating system with all low-level system dependencies. And at the moment, we have about 5,000 packages that we provide to our analysts. And these packages come from both external sources like CRAN or Bioconductor, but also we have a bunch of internally developed packages. So the key challenge here is that all these packages with their complex dependencies need to work together in a single environment. We also need some sort of release management and versioning to enable reproducibility. And as more and more compute platforms are emerging, as we have new infrastructure options, we have to design these systems with portability in mind. So in terms of release management, we are following the Bioconductor release cycle. And this means that twice a year, we issue a stable production release. And the stable means that all package versions are frozen for the next couple of months. And we only enable critical low-risk bug fixes. And this way, scientists can have some confidence that if they use these stable environments, their results will be reproducible, and they can switch them in case they want to, for example, go back in time and rerun something. At the same time, we normally have two environments which undergo constant package updates. So we have test which runs on a current release version of ARM. and then we have devel, which runs on devel version of R. And as we get closer to this, the test becomes UAT, and then the UAT is frozen at some point in time, and we get another stable release. Now, in terms of the build system for all this, the newest version, you can see the picture on the left, which shows simplified view of how it works. Is based on containers, and we're planning to fully transition to it as production at the end of this year. And everything is based on open source tools. So we're using Jenkins to orchestrate our builds. And the first step is to create the base Docker image. So we install all system dependencies for packages on this image, and then the continuous integration of packages themselves is managed by the ground package. So this package is available on GitHub at the moment, and the build is triggered every 24 hours. And what ground does is it will check source repositories of all packages that we have registered, and we'll see if any of the versions have changed. So if there's a version change, the package will be downloaded, it will be rebuilt, retested, and reinstalled. And most importantly, the same thing will happen for all reverse dependencies of this package. So for example, if we have an update to dplyr on CRAN, on which many packages depend, all these packages that make use of dplyr will also undergo rebuild. So if anything goes wrong, developers get notifications. We also publish detailed build reports, which show the state of the current environment. And packages which successfully pass through the pipeline are installed in external directory. And this way we can reduce the size of the Docker image. So you can imagine with 5,000 packages, this is quite large. And in terms of the artifacts produced by the build system, the key ones are the Docker image itself. So we're pushing it to registry, and it can be used later as a base for development. We're creating a package archive, which is exposed via web application, and it can serve as a source of dependencies. So I'll go back to this two on following slides, so in a moment. And the core of our interactive environment is actually a Singularity image, which we derive from Docker, and the installed package library, which I mentioned earlier, and which we can mount at runtime to Docker or Singularity images. So now, if you're a data scientist, you have two ways to access this environment. The first traditional one is via command line. So we use Furlani modules to override R and R script commands. And in this way, they run from inside of our Singularity image. So this is fully transparent to the end user. And of course, a more traditional way to use R is via RStudio, and we provide it on our HPC cluster through a platform called OpenOnDemand. So this enables you to define web applications, small web applications, and this is how it looks like in our case. So users can select the version of R of their choice. They can specify the resources that they require. And if they click launch, this will spin up the RStudio server on a compute node from our Singularity image. So there are several advantages to this. The first one is that we don't need to maintain and scale any central server for RStudio. And the second one, of course, is that our users can easily request more resources for heavy lifting in their interactive work. And moving all this to different clusters is also relatively straightforward, because it's basically a matter of copying image packages and a bunch of scripts. Okay, so moving on to the second part of the talk. So I will talk now about the software engineering workflows. So there are a couple of extra considerations here. So the first one is that we want to enable comparability. So for example, if someone is creating this Docker image for Shiny app I mentioned earlier, the result needs to be so the package versions inside this image need to be the same as in case of interactive environment, but of course we don't want to carry around 5,000 packages with us. Now it needs to be relatively easy to create such product-specific environments on the fly and easily share them with team members, because software development is normally a collaborative process, and you need to have continuous integration, which provides immediate feedback. So we cannot reuse our run build system, which only runs once a day. So in order to accommodate these needs, we created a system that's called very originally our platform, in short RP, and it integrates with Grun through shared base images and through shared package archive. Now, from developer perspective, this is a command line interface, and a typical workflow is that if you have a new R product, let's say Shiny application, you start by creating a Git repository, then you can clone it locally, and using our CLI, the first step is to register this product in the system. So the CLI will check what base images do we have available. Developer can choose one of them. This will generate a set of build templates. So this includes Docker file, template to install dependencies or define your tests, and a Jenkins file that controls the whole build process. And after filling and committing these templates to remote, this would trigger a build of the image. And during the build, we're using one of our standard base images, and these base images are configured to install dependencies from a stable repository of packages that corresponds to one of stable releases. So this is actually a key to enable consistency of these environments. And once this image is built, we run tests that are user-defined. We send notifications to a repository. And most importantly, we also register the commit which triggered this build together with an image tag in our service. And this makes it very easy to share these images with fellow developers. So it's sufficient to clone a product to check out specific branch. And then with a single command, we can get an image that corresponds to this branch. And after we have it locally, we can simply start local RStudio container. We can start the development, and whenever we push changes to remote, the build process will be triggered again, and we'll get a new image for a given branch that we are currently on. Okay, and to close the talk, I will just briefly show you how we're handling deployments for Shiny applications. So at the moment, any development team can request a product on Kubernetes clusters. So we have a couple of options depending on resource needs of the product, of the team. And after that, developers can simply use our command line interface to schedule a single-step deployment with one command. And there are two files that they need to get this done. So one is kubeconfig that they get after we create product for them, and another is a YAML configuration that describes their application, so they can get the default one using CLI. And if they need to customize something, they can, for example, specify resources for their containers like CPU or memory shares. They can define also things like access groups to restrict access to their Shiny application. And with these two files in place, the deployment can be done with a single command. So this will send our templates to the service. and send configuration to the service, and they would be used to fill the templates, and then Jenkins will simply schedule a deployment. And our Shiny apps are currently deployed behind Shiny proxy, and this has a couple of advantages. So one is that for every user that connects, we get a separate Docker container running. And at the moment, the number of users that can connect is limited by the size of the project that we provision, so we don't do any dynamic scaling, but this is totally sufficient for the needs that we have right now. So with that, I will finish the presentation. So I wanted to acknowledge colleagues from Genentech who were involved in this project, so Michael Lawrence, Rina Young, and a long list of developers from our side who contribute. So thank you, and if you have any questions, I will be happy to follow up on Slack after the talk.
Thank you, Dariusz. Yes, we will follow up with a Slack channel for questions.